Well, how excited are we to be here today? 2 years exactly to the day, really. I started my job 2 years ago on Thursday. We had one lecture. I don't know, were some of you at our last lecture that was in person? Yep, with Lawrence. And my anniversary was last week, so I know that it was the Saturday after I started, we had our very first lecture with me, and then all of a sudden we were thrown into shelter in place. So this is so special for me to see you all here. Thank you so much for supporting us in our virtual sphere. We don't really want to do that anymore. Let's hope we don't get another variant where we have to move everything back online. But I thank you again for being here. So before we get started, of course, I'm just going to do a quick land acknowledgement. So we recognize that Berkeley sits on the Hu-Chun territory, the ancestral and unceded land of the Ohlone people, the successors of the historic and sovereign Verona Band of Alameda County. This land was and continues to be of great importance to the Ohlone tribe and other familial descendants of the Verona Band. Every member of the Berkeley community has and continues to benefit from the use and occupation of this land since the institution's founding in 1868. By offering this land acknowledgement, the Berkeley community not only recognizes the history of the land in which we stand, but also recognizes that the Ohlone people are alive and flourishing members of the Berkeley and broader communities today. Thank you for allowing me to do that. So as you know, hopefully, or you're learning today, I know we have some first-timers here. Raise your hand. I'm going to do a classroom thing. Nice, excellent. So great to have you. So Science at Cal brings the wonders and excitement of UC Berkeley STEM research to the community. Of course, all of our events, guaranteed, are free and open to the public. They're geared towards public audiences, so we're very selective about how we have up here. So I'm so excited to have Raffaella here first to start us off. Of course, we do other types of events besides this lecture program. You can find us still virtually, as you saw as you were coming in. We had some virtual events that are still going on. And we're also out and about in the community. We're not yet at the farmers markets. They're still trying to keep everything kind of slow-paced, but we'll be back soon. We're going to be at the first Friday in March, everybody. Oakland's first Friday. Come visit us. We'll have some STEAM, some scientists and science artists there. And we will also be at the Bay Area Science Festival, so events both in Berkeley and in San Francisco. So we'll keep you up to speed on all that we're doing. I want to say thank you to Berkeley Community Media, who's here and who's been here with us for several events. Thank you so much for filming and getting everything live for us. So we're going to be very grateful for them. They do that in-kind donation to us by being here. So thank you, Berkeley Community Media. I want to thank the Science at Cal Advisory Council. We have Dan, hi Dan, and is Rachel here? Rachel! Hi, Rachel. As you all know, Rachel was the director of Science at Cal for many, many years, and we are so grateful. Let's give Rachel a round of applause. Thank you, Rachel. I didn't see you come in. I was afraid you, I missed her. I also want to thank the UC Executive Vice Chancellor and Provost for their generous support of this program. I want to thank everyone who not only has donated today, but who has donated in the past and who will be donating in the future. I have a box here if you want to put checks or cash in this box. So it'll be with Elise on the table in the back. We also have somebody from the Lawrence Hall of Science, because I'm not sure if you remember, but 2 years ago we did make an announcement that we are now housed within the Lawrence Hall of Science. So we have Tim here from the Lawrence. So if anybody would like to talk about sponsorship or how you can support Science at Cal on a larger level, we'd love to have that conversation with you, because our money will eventually run out. And again, we want all of our events to be open and free. That's really the groundwork of what Science at Cal does. All right, so I think without further ado, I'm going to go ahead and introduce Raffaella. So Raffaella Margutti received her undergraduate degree in astrophysics in 2006, magna cum laude, and her PhD in physics and astronomy from the University of Milan in 2010. Margutti is a Sloan Fellow in physics and a CFER Global Scholar in Gravity and the Extreme Universe and she won that in 2019. She received the 2022 New Horizons in Physics Prize for her leadership in laying the foundations for electromagnetic observations of source gravitational waves and leadership in extracting rich information from the first observed collision of 2 neutron stars. She joined UC Berkeley Astronomy Department last year. So we are so excited to have her not only here today, but also on campus. So I will let her take it away.
Thank you so much for being here with me today. It's really exciting. And I would like to thank my students also for coming. I really appreciate your support. So if you were wondering what on earth you were hearing and listening while you were entering this room, that's what it was. So this is part of my artistic and my music side. So I'm working with a composer, and we're trying to translate stellar explosions into music. And this is the artistic side, but there is a serious side, which is we are trying to make these explosions audible for everybody. So that's what it was. So we start from the end today. So we start from the death of massive stars. And what I want to do with you today is taking you on a little tour through what I define to be a very special time in astrophysics. I call it the Renaissance of Astrophysics. Why? Not because we were dead before, but because what is happening right now in astrophysics is that all the walls between different disciplines are falling down. And this was one of the key engines that enabled Renaissance in my beloved country, Italy, if you didn't get my little tiny accent that I have, right? All right, so let's get started. So I want to take you to the limit of our knowledge. I want us to understand where ignorance is, the beautiful ignorance that is the fuel of our research. So let me be very clear. So where is that ignorance in my field? So we do know very well that we do have massive stars, and that we do know very well, we can see them exploding. So that we know for sure. However, we still don't know what do they leave behind. Do they form a black hole? Do they form something else, like a neutron star? We don't know. That's the limit of our knowledge. We do know for a fact, though, that massive stars, and when I say massive star, what I mean like 10 times our sun, we do know that they like to hang out in binaries. And sometimes they explode, the first one explodes, and let's assume that produces this very compact body that we call neutron star. The second one also explodes and produces a neutron star, and sometimes this system is able to survive. We will see in a little while how difficult it is for this couple to survive until the end. And these 2 neutron stars, though, they can't stay there forever. They lose energy, and we will see that they lose energy through gravitational waves. We will learn what these are. And at the end, they merge. They merge, and they form something that we don't know what it is. So here is another limit of our knowledge. So here is where ignorance is again. So what happens during this very violent event of the merger of these 2 neutron stars, and how that appears in photons? How does that appear in the light that we can capture with our telescopes? This is what I would like to explore with you today. So the key point here is that the entire field of astrophysics has a huge knowledge gap, but now is a very special time for humans because you can fill this gap not only with light, but with something that is neutrinos, so these very, very little particles, and gravitational waves. So we are living through a very, very special time in human history. For the first time, we can combine light, we can combine neutrinos, we can combine these gravitational waves, and we put everything together to understand what is happening in the distant universe. And I feel I'm very privileged to be living through this new era of astrophysics that we call multi-messenger astrophysics. All right, So here is what we'll be talking about today. What you're looking at is not reality, is an artistic impression. But we have these two neutron stars that are rotating around each other, and they lose energy, and at some point they merge, and they produce something extremely violent. So I want you first to have a look at the big picture, and then we will try to understand what did we see and how that happened. But I wanted to first have an idea of the big picture. So we have these two bodies, they merge, they produce something violent. And at that point, you might ask, why does that matter in the first place? Why should I care? So I'm going to give you a little bit of context to understand why understanding this process is so important. So let's first ask to the first question, how do we form one neutron star? And we have a very good answer to this, because we can see that in our own galaxy. So we do know for a fact that the explosion of massive stars, this is again an artistic rendering that will end with a true image, the explosion of a massive star can produce a neutron star here, and what you're seeing here is the Crab Nebula. I'm sure that some of you have recognized the Crab Nebula. So we do know that if we explode one star, we can produce a neutron star, and here you're looking at real data. So you're looking here at an image that has all the wavelengths, so all the types of light that we can put together. And here you see the same object into different types of light, like putting on different types of glasses. You can see it through in different ways. And you can see that at the center here, there is something that shines with very high energy radiation, these gamma rays. And that thing that shines so widely is a neutron star. So this was an explosion in 1,000 years ago, in 1054. And we can say, yes, we do have a neutron star right there. So we can answer that question. So the thread number one is, how do we form a neutron star? We explode a big, massive star. Great. But we need two, right? Because I told you that we will be studying the merger of two neutron stars. So how do we form two? Well, let's assume that we start off with a system of two stars, one a little bit bigger than the other. And it just happens that in the universe, bigger stars, they use up their fuel faster. And their fuel is hydrogen. They do fusion of hydrogen. But the more massive you are, the faster you will be in using up all of your budget. So the biggest star will explode first. Then we wait a little bit, and let's assume that even the second star is massive enough to also explode. And then at the end, we will be there with two neutron stars. However, as you might guess, this explosion of the entire star releases a lot of energy. So it's something extremely violent, extremely violent. So, and it turns out that it's difficult for the couple to stay together. So if I was born with a bigger star and my bigger star companion explodes, it will be difficult for me to stay attached to whatever is left behind of that star. And only some fraction of the stars, some few percentages, they stay together. Same thing for the second event. It's difficult to stay together if the other one is exploding. And at the end, it turns out that even when we start off with a perfect system that can produce two neutron stars, it turns out that only 1 out of 100,000 can make it to the end. Okay? Okay, so right now, the message that I want you to take home is that these things are rare. So this collapse, this merger of two neutron stars, is something that is rare in our universe. All right. Here's the other important piece of information. Now, let's assume that we have been very lucky, and our two stars were able to survive. And now we have two neutron stars. Can they just stay there and live happily together forever? The answer is no, they can't. So the reason is that these two bodies are extremely compact. this is the place where we can really experience gravity in its most extreme manifestation. So these two bodies are rotating one around the other, and while doing so, they are losing energy through gravitational waves that are ripples in the fabric of space-time. All that matters is that these two bodies are losing energy. And here, it's not important that we understand exactly what we are plotting in this plot, but here, the year is literally our calendar years. And what you have on this other part of the plot is a quantity that quantifies how close these two neutron stars are getting because they are losing energy. So they start out far away, and they start losing energy, they get together. And if you look at the data point, and you can see is that the prediction from the Einstein general relativity theory, you can see that general relativity tells us very, very well what's going on. So, very important message. We do have these two neutron stars, and they can't survive there forever because they are losing energy, and that makes them getting closer and closer with time. Yeah? Awesome. So let's add another little piece to the puzzle. Since the 60s, we do know of something that we called gamma ray bursts. There are bursts of gamma rays that were found for completely different reasons, but thankfully they were not of human, related to anything human. They are astrophysical. And these type of sources they produce very short pulses of gamma rays. When I say short, I mean few seconds. And to give you an idea how much energy is there, is more than what the sun will produce in its entire life. So these are extremely violent phenomena. And we did know of them, and we did think that they could be related to the merger of these two neutron stars. So we speculated that a theory that can explain this extremely violent phenomena can be the merger of a neutron star. That was a theory. All right. So now let's stop and think for a second. What do we know until now? So what I've told you is that we do have neutron star couples in our universe. Second, they are rare. It's difficult for the system to survive, so those are rare systems. But when they are there, they can't stay there forever, and they merge. And when they do so, we think they would produce something extremely violent that we call gamma ray bursts. This is all we knew until 2017. And what I want to do with you today is to add yet another piece to this puzzle and then see what happened in 2017 that allowed us to put the entire story together. The last piece of the puzzle is the following. So when I was a grad student, people would tell me that we could form the entire sequence in the periodic table just with a combination of things, including stellar explosions, and that the heaviest elements in the periodic table, they were all coming from stellar explosions. However, with time, there was a shift in the thinking that for some of the heaviest elements, let's name some of them that are particularly famous, like gold, platinum, those stuff. There was a shift in the community where we started thinking maybe we do need neutron stars that merge to produce some of these elements. And again, this was a theory before 2017. We thought that could be right. And what I want to tell you today is the story of something very special that happened on August 17th, 2017, of how all of these threads were united and how that event, that is still the only time we could capture gravitational waves and light together, how that permanently changed our view of the universe and the way we do investigations of our universe. Okay, so I'm going to tell you the story. I'm going to tell you how it happened, but also I also want to give you a little bit of a flavor of the real life. I don't want to give you just cold science. I want to tell you what happened that day, how we tried to go after the source, and give you some little tiny fun details. So let's get started. So first of all, what you're looking at here is the gravitational wave signal. And you have here different types of events that were detected producing gravitational waves. And the way they're named is gravitational wave and the year, month, and day. And what I want you just to take home from this slide is that before 2017, starting 2015, we started being able to detect gravitational waves coming from black hole mergers. So it was 2 years that we could see these signals. And then, in August 17th, look at this, it's just 3 days after this other event. This is important for my life. But look at that. Look how much longer is this signal. It doesn't take no scientist to say, if I look at this thing, so I look at this one, they are different, right? Okay, great. So the reason why they look so different is because these events did not include a neutron star. Instead, this one is the result of a neutron star merger, so they appear completely different in the spectrum of the gravitational waves. So the story of this August 17th start like this. So it starts with the detection of a signal in gravitational waves that was remarkably different from anything we have seen so far. All right. And that was a clear signal that two neutron stars had merged. All right. So let's place what we knew based on that signal that you have seen on this plot. And what you have here is just all the masses of, and here it's in units of the sun, so the sun would be here, of things that we know in the universe associated with either neutron stars or black holes. And you can see that there are two groups, right? It seems like there is a group of stuff here that we associate with neutron stars and a group of stuff here that we associate with black holes. And the two ones that merged, we can place them. We can understand how massive they were from the gravitational waves. So I can tell you that these two produce something that is somewhere right there, but I still can't tell you what is that new thing. I just know that it's in between these two worlds, but I don't know if it is a neutron star or a black hole yet. All right, so let me add some real life part of this story. It's 6 a.m. on Earth. I will talk Pacific times. So it's 6 a.m. on August 17th, 2017. And we received the alert from the interferometer from the Gravitational Wave Telescope. How do we receive the alert? On the phone. Later on the phone. And actually, if you want to get those alerts, you can. You can sign up, and you can actually get paged with a very nice LIGO up. So we get that 6 a.m. Trigger, and scientifically, when we look at the gravitational wave signal, instead of looking at the wiggle that I showed you, we look at this type of plots. And all that matters is that whenever this ends, it's the time when the two neutron stars become something else and they merge. So 0 here just means merger. All right. And right away, we looked at the signal from Gammaray spacecraft. So keep in mind, I talked about Gammaray bursts, and now look at that, 2 seconds, right? Just 2 seconds after the gravitational wave merger, we have these little spikes. Those, even if they look almost nothing, this is an impressive amount of energy coming out in the gamma rays, and this was just 2 seconds afterwards. So we have a gravitational wave signal, and 2 seconds afterwards, we get the alert, hey, there is also a gamma ray burst. And more than that, we can talk about where in the sky these two signals were coming from. And here you have think about this as a map in the sky. And the things that matters is that the gravitational waves are telling us the localization in green. They're telling us, look somewhere here or here. And the gamma rays are telling us, look somewhere there. And let me try to quantify better what that means. So if we zoom in, the area where the gamma rays and the gravitational waves were coming, was of the order of 28 square degrees, which I assume doesn't mean much to many of us. But think about the size of one full moon. 100 of those full moons is the area in the sky where gravitational waves and the gamma rays were telling us to look. So for astronomical standards, it's huge. They tell you somewhere there. Look somewhere there. Good. So it's 6 a.m. And we had no telescope that we could put our fingers on, and actually nobody in the world had. And we had to wait for the sun to set. Our telescopes were in the south. This event was in the southern hemisphere, so we were really well positioned. So we have 11 hours where we're waiting for the sun to set. It might sound like we were relaxing in these 11 hours, but it was really hectic. A lot of things were happening in those 11 hours. We were trying to think, what is the most intelligent way we can tile that field? That field is very large. Where do I start from? And when you say we, I talk first about my team, but it was 1,000 people that was doing this type of race. We all wanted to find the light coming from this gravitational wave merger. All right, so it's 11 hours. We are still waiting for the sun to set. And the instrument that we were using is in the south. The name is Dakam. It's an instrument that has a big field of view. It means that it can take pictures of a big portion of the sky at once, and that's why we wanted that. All right, so here's how we were set up. Of course, we have been preparing for years and years to this event. And our team setup was the following. This is how a gravitational wave observatory looks like with these very long arms. We get the alert. Then we have our big field of view telescope that starts tiling the field, starts looking for something new in that field. Great. And the idea is that after this thing finds something, then we can repoint all the other telescopes that have very narrow field of view. Yeah? So the sequence was LIGO, then Dakam, and then we trigger everything. Everything else we could put our fingers on. That was our setup. And on paper, it looked like, oh, easy. You got the alert, then you do this, you do that. Simple. Awesome. So we were here, we were waiting. So here is what happens. Just a few minutes after the sunset, we got an email from our collaborator that said, holy cow. Let's say holy cow. Look, check out, this is the name of a galaxy. Check it out. And I want to emphasize one thing, that we've been spending a lot of years putting together software to do all the fancy things about finding differences automatically, and we thought we were all set. Okay, so this was done by eye. This was done completely by eye because Ryan did not trust our software enough. And by the way, Ryan is now a research faculty here at UCB. All right, so what made Ryan coarse? Well, he was looking something like this. This was what we call reference image. You're looking at a galaxy. This is a galaxy. And then look at what he found. Took. Gonna go back. And after I show it, it's easy, like everybody can spot this new thing, right? That's what made him extremely excited. And this is one of the 6 independent discoveries of the light, optical light coming from a gravitational wave source. This is the first time and only time that we were able to do it. So this is how it all started. So now let's see what happened afterwards. As I told you, once you can say, look here. So we started off from a field like that, and Ryan said, you should look at this specific little thing. All right, so now it's easy. So we can just take all of the programs we had on everything and say, hey, now everybody, you stop doing what you were doing and use Lou and get on target for me. That's how it works. And that's what we did. And we just started staring at that simple, that little part of the sky. All right. So here is what happened. And again, I want you to go back to the big picture here. So what we knew that most likely what we were looking at were 2 neutron stars colliding. And we had some expectations for what type of light we should be detecting. And we knew that we were dealing most likely with something that had many different components, which is why we bother triggering things from the optical all the way to the gamma rays. So what I want to do with you is now telling you a little bit more of what is what on this picture here. So as I said, what we were expecting, and this is based on fantastic work by theorists, were two components of light, two types of light we were expecting. One that was coming from all the directions, and that is related to the place in the universe where we are forming heavy elements. A good way, the way I translate it is that this is where gold is formed. And then we also had something else, which is light very, very beamed. We call it jets. Extremely energetic. Those are the gamma ray bursts I was telling you before. Physically, they are jets. And they travel at the speed of light, roughly. So this is what we were expecting. So let's go and see the timeline here. So we have a first discovery that tells us we point here. So we start going after with everything we could put our fingers on. And we start getting on target with radio. And we got really excited, really excited. We looked at that thing, and we started jumping. We thought we got the radio counterpart. And then we put coordinates on it. And no, your counterpart should have been in the yellow part. Here, instead, we are looking at the galaxy, at the outer galaxy where this neutron-star merger happened. So no, a lot of excitement, nothing to see. All right, so let's start to get some X-rays. And as you can see, it takes way longer to repoint an X-ray spacecraft. So we alerted the spacecraft right away, 0.5 days after the merger, but it took 2 days to get on target. Those are the limitations that we have right now. And here is what we found. Nothing. I can tell you these two little photons, they are noise. It's nothing, nothing whatsoever. However, the optical people instead, the optical people were having a lot of fun because on their wavelength range, they could see a lot of things happening. And here, I'm using a simulation here by Dan Kaysen, professor here at UCB, that is the one that produced the theory that allowed us to interpret what you're looking at here. This is how the light from the part of the sky where 1708-17, the gravitational wave merger happened. How did it evolve with time? This is the thing that produces these heavy elements, this gold, platinum, all that stuff. And I want to emphasize how remarkable the predictions were in this case. This is one of the cases where theory really was able to guide us in our work. And while I can't tell you into the details why we can say with confidence that this produced these heavy elements, just trust me that the shape of these wiggles here is what told us that yes, this is a place in the universe where we are producing these heavy elements. We would not have this type of shape. It would not be in this part of the spectrum, which is near infrared, unless we formed these heavy elements. So studying these wiggles, and again, this is a beautiful prediction by Dan Kaysen, studying these wiggles, we can actually understand how much of these heavy elements we can produce. And I can tell you right now that neutron star mergers are most likely the place where most of our gold and platinum are formed. So if you're wearing something that is made of gold or platinum, think about it, how beautiful that those elements were at some point formed in a neutron star merger. I always find it fascinating, right? All right, so let's go fast forward here. We tried hard and hard to find these X-rays, and 2 weeks after the event, finally, we found something. And when I say something, these are 10 photons. I can count them, and I can name them. These little 10 photons these are the first X-ray photons from a neutron star merger that we can say with confidence are coming from a neutron star merger that we could detect. Great, so we started getting excited. Also in the high energy part of the spectrum, we started getting excited. And guess what? We found X-rays, and we also found the radio around the same time. We started getting very excited, and as it always happens, the universe does something for you, and in this case, the sun gets too close. And that's a problem in the X-rays. It's a problem in the optical, but thankfully, it was not a problem in the radio. So radio could look at this event while the sun was in the way for all the other wavelengths. All right, so let me walk you through what you're looking at there. So long story short, I'm here 3-4 years almost after the event. It's more than 4 years, actually, after the event. Yeah, completely lost sense of time with COVID. All right, so, and what are you looking at here? So here those are light curves. It tells you how the light coming from this event varies with time in different frequencies. Here is X-rays in blue, and it goes all the way to radio. And the only thing that I want you to bring home is that it went up for 160 days, and then it went down. So this thing re-brightened, and then it started falling down. And the reason why this is so important is because this behavior is very much related to what is happening in this extremely powerful jet. And I will try to give an intuition of why the fact that we did not find X-rays and radio at the end was so beautiful. I was very happy that we didn't have a radio and X-ray detection at early times. And here's the reason. So for gamma bursts, when we detect gamma bursts, the very powerful ones, we tend to detect them when we are aligned with that jet. But those jets are extremely collimated, like really, really, really tiny jets. So you need to be lucky to be on their line of sight. And if you think instead that you're trying to detect something not based on their gamma rays, but from something else, and in this case, gravitational waves, that don't really know much about where the jet is pointing, then it makes sense that most likely we would not be looking at the things down the jet, but we should be looking at things from some other direction, right? Probabilistically speaking, we will be somewhere else. All right, so in that case, if this is true, here's what happens. So suppose that I'm going to use you too. You are my source, and I am your observer. If I'm looking at you and you're looking at me, at the beginning, I see you. But now let's assume that I'm right here, and you're producing light in that direction. I don't see you. But here's what happens. Now I do the gamma ray burst, and you do the observer. I start producing light right there, but as I expand, I become less and less collimated. So at some point, you see me, right? So at the beginning, you don't see me, but as I decelerate in the environment, you see me. Awesome. This is exactly what is happening here. So I just explained to you in one sentence the lack of relativistic beaming is how special relativity works. So we are here, we expand, and we come into the light nanosite. So now, if you look at this light curve, now it makes sense, right? At the beginning, there is a little light or no light, and then a little light produced that intersects the observer, but then the light opens up, and we can see the entire jet. So basically, by modeling, by doing real math on this jet, we can understand how narrow was the jet, where we were looking at it. I can tell you we were around 25 degrees away from the core, and we can understand how much energy was there. And that's why I can tell you with high confidence that this event is just like the same of the gamma ray bursts that we started detecting in the 60s, and that were a huge mystery until now. All right, so it goes up and goes down. And if things are well behaved, light should just keep decaying with time. Nothing else is expected to happen. And here is where things that just happened like 1 month ago start to matter. So I'm going to share with you super fresh news. So this is the expectation, and we were super happy. We could interpret kilonova is just the name of the platinum gold producing part. And we could say, yes, there is a ultra relativistic jet. This is what we call gamma ray burst. Great. all the puzzle is all solved, happy, move on something else. Not so easy. So we repointed, again, at Chandra, which is a very sensitive X-ray spacecraft. And look at here. Now you know there are a few photons, but they're really important. Those photons should not be there. And that's beautiful. It means that the theory that we have is not complete. So why this is so beautiful, and this is just to emphasize, you have a model that is the blue one, and you can see that data start to deviate. We have too much X-rays than what we were expecting. The reason why this is so, in my opinion, so extraordinarily exciting is because, as I kept telling you, we have no idea about what is the nature of the new object. Is it a black hole? Is it a neutron star? And these X-rays might be the first signal coming from the newly formed black hole. So the reason why I'm so excited is because we might have an opportunity to answer to that really deep question about what is formed after the neutron star merger. So stay tuned. We have a press release coming out in the week of February 22 about this event, so that you will know more about this excess of 10 photons that should not be there. So where do we go from here? And I'm at the end, I promise. So where do we go from here? We saw light from a gravitational wave source only once. So the first thing that comes to the mind of everybody is, I want more. We want to find more of this light coming from gravitational waves. And LIGO, the Gravitational Wave Observatory, will turn on again in December 2022. And of course, we want to keep monitoring. We want to get more data of the neutron star merger of 2017. And I want to share with you what we are planning here in Berkeley. How are we getting ready to play this game of multi-messenger astrophysics? And I just want to share with you that we are starting a new survey. So we have a new telescope in the south, a collaboration led by Peter Nugent at LBNL. And we will be using this telescope to do that job of tiling big parts of the sky and understand where we are going. So we are really getting ready and to play the game of multi-messenger astrophysics, this entirely new way we can study our universe here at Berkeley. And I just want to end here, but I study the end of things, but the way I look at it is the beginning of a new type of object. I want to thank you, and I'm happy to take your questions. Yeah, I see a raised hand there.
So earlier in your discussion, you talked about the two stars that were orbiting each other, and they had supernovas, they formed neutron stars. You said it was 1 in 100,000 possibility to survive that process. Is it known what the initial conditions makes it survive, and which ones do, which ones don't?
Yeah, so the question is, I'm going to repeat it for the recording. So the question that was asked was, we started off with 2 massive stars, and I told you that 1 out of 10 to the 5 are the systems that make it roughly all the way to the end. And the question is about what are the initial conditions that would give us a higher chance probability to arrive at that stage. So first of all, you need to start off with stars that have the possibility to leave behind a neutron star. And you might think, well, okay, I'm going to go with stars higher than 8 to 10 solar masses, which is what we think can produce neutron stars. But what you don't want is that thing to produce a black hole, because that's the other possibility. These massive stars can give you a black hole. And the answer to which massive star gives you what is unknown right now. So that part of the story is not known. Other parts about how close you need to start your binary, those are known, because I glossed over one detail, which is that even if you arrive at the end and you have 2 neutron stars, then you want those 2 neutron stars to be close enough that they can merge on a time scale that is relevant for the universe. You can end up with 2 neutron stars that will not merge on the Hubble time, so it will be irrelevant. So the answer to your question is yes and no. We have parts that we understand, there are parts that we definitely do not understand. Yeah. Other questions? I go there.
If black holes are more massive, why is it that neutron star collisions have more violent results than black holes? So neutron stars have more violent collisions than black holes.
Ha. So the question, and tell me if I get it right. So the question is, if we have why a collision between two neutron stars is more powerful than a neutron star plus black hole or black hole, is that right? Yeah. So it depends on. So from an energetic perspective, this is not necessarily true, but the fact that neutron stars are made of matter allows them to dissipate energy into light. So you can see it easier, in a more easy way. However, I have to tell you that you're very right, that you can end up your life with a black hole and neutron star system. We did see those in gravitational waves. Those systems do exist. We failed to find light coming from those systems, because in that case, the black hole can basically just eat the other star, and that's it, and nothing escapes. It's a fantastic question. Yeah, thank you. Other questions? Well, a lot of questions. I'll go there.
Does the distribution of heavy elements in the universe as we understand it roughly correspond with the frequency and distribution of neutron star mergers?
Yeah, so another way of asking the question is, so can neutron star mergers just account for all our heavy elements in the universe? You're asking one of the big questions of the field. So I can tell you that if all neutron star mergers look like exactly as the one that we have seen, the answer is yes. But I also have to tell you that we do have strong signals telling us that not everything looks like this one. And in that case, there is space for other types of collisions to produce heavy elements, but also there is space again for these beautiful stellar explosions, which is another side of my investigation. Another question? I'm gonna go there.
For the X-ray emission around the newly formed accretion disks, just thinking generally about what accretion disks or what types of radio emissions, what type of emissions should there also be an associated radio emission as well?
Okay, this is the question is clearly coming from somebody that has some training in astro. So the question is, so and is very correct. So I told you that those X-rays that we see might be a signature. These 10 photos that should not be there can be a signature of this new black hole that was formed. And specifically, what is shining is not a black hole, but is an accretion disk. So it's like a disk of matter that this black hole is basically eating up with time. And the question is, if there are X-rays coming from that disk, which is what we usually see, shouldn't there be radio also? The answer is yes, but is below our detection threshold. Yeah, so you're very right. It's a fantastic question. Yeah, you have another question right there?
If I understood you correctly, at the end of your talk, you suggested that the gravitational wave observatory is shut down and will resume operation in December. Why did it shut down, and what needs to happen to start it back up?
Yeah. So why they shut down? For a very good reason. They are improving their sensitivity. And that's the main reason why they're shutting down. And so they want to be able to see farther in the universe so that they capture more. Yeah. And I did not repeat the question. The question was why LIGO is off. So why the Gravitational Wave Observatory is not on right now. They are trying to improve their instrumentation. And there was a second half of the question that I forgot.
What needs to happen to start it back up?
Yeah, I actually don't know exactly what they're doing right now, but I know that it's an improvement to their sensitivities. Yeah. Also, I have to say, LIGO is going to be joined by, when I say LIGO, in reality I'm unfair to Virgo, which is the Italian Gravitational Wave Observatory, and there is also CAGRA, which is a Japanese effort that will join during the next observing run. Yeah. Other questions?
What's the nature of the 2-second delay between the gravitational wave and the electromagnetic signal?
The question is, there was a delay of 2 seconds between the gravitational waves and the gamma rays that we have seen. So why that is so? This is another great question. So first of all, those 2 seconds delay is one of the most important multi-messenger physical parameters. We did not know of that before because we have never seen gravitational waves and light together. So coming to the question, so why there is a delay to start with? There are multiple explanations, but one that I find the most likely is that it takes time. While gravitational waves, they go through stuff, it takes time for light to escape. So you needed 2 seconds for that light that was produced there to be able to escape its own merger environment. And that basically tells you where those gamma rays are produced versus where the gravitational waves were produced. So it's just a matter of transparency. You were not transparent during those two seconds, but it's a very beautiful physical parameter. And there's a lot of investigation about those 2 seconds. Yeah. OK, other questions? I see it right there.
Yeah. Hi. I was wondering how James Webb would help, like the James Webb Space Telescope would help with finding the nature of neutron star mergers.
Yeah, so the question is how James Webb, which is the new observatory infrared telescope of NASA, will help. So James Webb will be transformative for this science. The reason is, when I told you that from the wiggles, I can tell you that there are heavy elements produced, where James Webb will do that at a completely different level. And it will really be able to tell us the details of that infrared light in ways that we have no access right now. Yeah. Yeah, that's another great question. Other questions from the audience? All right, I'll take yours.
Okay. That 2-second delay, does that have, or is that influenced at all by the matter of the neutron star?
Yes, the question is if the 2 seconds delay is in any way influenced by the matter of the neutron stars. The answer is yes. Yes, yes. If the composition of the matter would be something else, that would change. Yeah, is it basically the transparency to the gamma rays? Yes, that's another technical question. All right, any other question? Oh, okay, Tian, of course, yeah.
Hey, so my question is, so we have two neutron stars, and they merge, and somehow they produce a gravitational wave. So if there were 2 stars who have the same mass with the neutron star, and what if they also do merge, will we get the gravitational wave?
Okay, tell me if I get this right. So the question is, those 2 neutron stars had a mass of around 1.5 times our sun. If instead of having 2 neutron stars, I had 2 stars that were not neutron stars of the same mass, would I get gravitational waves? Is that a question? The answer is no, because the reason why the answer is yes, but not detectable. That's a correct answer. So, and the reason why it's not detectable is because the neutron stars not only have that 1.5 mass, solar masses, but all of that mass is in 10 kilometers. So the way they perturb space-time is really, really, really extreme compared to what a normal star would be able to do. So you really need, right now, we can only detect neutron stars and black hole merging for that reason. Yeah, one question more? Yeah.
Hi. So you mentioned that in the initial, like in the very beginning, when Ryan identified the optical image, and you mentioned that he didn't trust the system and that he actually went and looked at the features. I was wondering if there's anything that we're like doing right now to bridge that gap or anything that can be done.
Yeah. So the question is, so for that specific event, Ryan did not trust the software that we had in place, and he started matching the images by eye using images that we had access to. And the question is, are we now better prepared? The answer is very much yes. So what I glossed over a little bit is that in 2017, this was I think the last week that LIGO, Virgo were on. And also the other detail that might not look so important, but there was a solar eclipse a few days afterwards. And why that matters? Because nobody was working. And then so the thing, what I'm trying to convey is that, first of all, we were not expecting to find a neutron-star merger in 2017. and definitely not during the last week of the run, definitely not a few days before the solar eclipse. So while here, I tell you the story, and it looks like elegant and polished. It was a complete mess. It was a complete mess. The most beautiful mess I've ever been part of, but really, really messy. So yes, we are better prepared. Yep. One last question? Yeah?
Yeah, the question was, I think towards the end you talked about the next steps is digging deeper into the nature of the compact object. You said something about February 22nd and some announcement. I was trying to get, like, is that what is going to be discussed in your sort of your next phase of research on this? Or
Yeah. Okay, so the question is so we are getting more and more data about this event and try to probe deeper into the nature of this event. And your question is about what are our plans to do better? Okay, so right now, this neutron star merger was really nearby. On astronomical distance scales, this was really, really nearby. In spite of that, it's right now only detectable, is only bright enough for one spacecraft for everybody, which is Chandra. So the only hope that we have is that whatever is giving us those 10 photons more will re-brighten in time so that other things can have a pick of that. But I also have to say that right now, the rate of evolution of that object is very slow, which means that the next generation of X-ray spacecraft, the next generation of radio antennae, can actually, if they happen for real, they could keep detecting this neutron star merger until they retire, which is a long time. It was a joke. Yeah, but in principle, if we do well and we can put in orbit the next generation of spacecraft and make happen the next generation of radio antennae, we should be able to keep getting information from that object for a long time. Yeah. Okay, thank you so much. Thank you so much.
All right. Before we go, everyone can hear me? Before we go, I just wanted to say, because I said thank you to the council members who were on my list, but there are actually more in the audience because I can see you. So Kathy is our chair, Kathy Collins. Thank you, Kathy. And I heard Carlo's here. Thank you, Carlo. Who else is here? Anyone else that I'm missing? Because if I say thank you to someone, oh, Rachel? I thanked Rachel. But we can always thank Rachel again. I want to, of course, everyone, let's give another thank you to Raf. She was amazing, kicked us off in such a spectacular way. We are thanking her with a Science at Cal shirt, so thank you again. And we will see, this will be our standard room for here on out, except next month is taken, so we're back in GPB, where we have historically been in genetics and plant biology. You'll learn all about it next time, but then we will be back here. Yes, question? It will now be on the second Saturday from here on out, and the reason for that is we had already scheduled our virtual events on the Thursday, and they were just too close together. And I also want to mention that Steve Croft, who started this lecture series, apologies he couldn't make it today, but he'll be at the next lecture to say hello to all of you. So thank you again.